For 27 years, NASA watched it and saw nothing unusual. Just another rock, catalogued, tracked, filed away as harmless. Then, in August 2025, it wasn't where the math said it had to be. Not close, not within any reasonable margin of error. Off by an amount so extreme that the deviation itself became the story. This is not a tale about a lost asteroid. It's about a blind spot, one that may already be sitting inside the models NASA uses to predict impact risk for nearly 38,000 near-Earth objects currently in the catalogue. The object is called 1998 SH2, and for 3 decades it hid what it actually was in plain sight, using a trick no telescope could catch until it was almost too late. What gave it away wasn't a bigger rock, a brighter light, or a closer look. It was a push. Small, invisible, and nearly impossible to explain. 1998 SH2 was discovered in 1998, and from the very beginning, it behaved exactly the way an asteroid is supposed to behave. It circled the Sun roughly every 4.5 years, following a path that gravity alone could explain. No surprises, no anomalies, nothing that would make a scientist look twice. For nearly 2 decades, from 1998 to 2016, telescopes tracked it consistently, refining its orbit until researchers felt confident they understood exactly where it had been and exactly where it was going. It became one of thousands of quiet entries in a catalogue most people will never hear about, filed under boring, filed under safe. But here's what nobody realized at the time. After 2016, the observations simply stopped. Not because anything went wrong, but because there was no reason to keep watching something so unremarkable. 1998, SH2 completed 2 entire orbits around the Sun without a single telescope checking in on it. 2 full loops through space, unsupervised, unmeasured, unquestioned. And somewhere during those silent years, something was already changing. Something was already pulling this object off the path predicted purely by gravity, and there was no one there to notice. The drift didn't announce itself. It accumulated quietly, invisibly, waiting for the next time anyone bothered to look. That moment finally came on August 28, 2025, when 1998 SH2 swept within 2 million miles of Earth. And that was when the story fell apart. Researchers preparing to observe 1998 SH2 during that close approach turned to one of the most powerful tools NASA has for tracking objects this close to Earth, the Deep Space Network's planetary radar system. They calculated exactly where the object should be, factoring in the gravitational pull of the Sun, the planets. Everything physics said should determine its position down to the smallest detail. Then they pointed their instruments at that exact patch of sky. And it wasn't there. Not slightly off. Not a rounding error. Nothing. A silence where a signal should have been. For a moment, the obvious explanation was human error, a miscalculation somewhere in the decades of accumulated data. But the more the team checked, the less that explanation held up. Using optical astrometry, precisely measuring the object's position against the fixed backdrop of stars, researchers eventually located it again. And when they did, it had moved significantly beyond where gravity alone could have carried it. The scale of that deviation is what turned this from a curiosity into a discovery. The object's position was off by 19 standard deviations from its predicted path. In scientific terms, that number doesn't leave room for coincidence or measurement noise. It leaves room for exactly one explanation. Something physical, something real, had been quietly steering this object off course. Not a mistake in the math. A force the math never accounted for. And once that possibility was on the table, everything about 1998 SH2 needed to be reconsidered. David Farnokia, a navigation engineer at NASA's Center for Near-Earth Object Studies, led the team trying to explain what they were seeing. And what they landed on wasn't exotic physics or a flaw in the equations. It was something far older and far stranger. A process that happens quietly across the solar system every single day. As 1998 SH2 orbits the Sun, sunlight heats a mixture of ice and rocky material buried beneath its surface. That heat turns the ice directly into gas, and the gas escapes, venting outward into space. That venting acts like an incredibly weak, uneven thruster, pushing the object just slightly off the path gravity alone would predict. This is exactly how comets behave. It's the same mechanism that has explained cometary motion for centuries. Farnokia and his team recognized that the perturbations affecting 1998 SH2 simply weren't compatible with it being an asteroid. They suspected they were looking at an active comet in disguise. But here's where it gets strange. When most comets vent gas this way, the escaping material forms a bright, unmistakable tail and a glowing coma around the nucleus, something visible from Earth with a decent telescope. 1998 SH2 produced almost none of that. The gas and dust venting off its surface were so faint, so minimal, that its tail and coma were essentially invisible to most observatories. It had been quietly leaking evidence of what it truly was for years, and nobody had the equipment sensitive enough to catch it happening. At this point, the team had a hypothesis, not proof. And that's exactly how science is supposed to work. You form an explanation, then you go test it against reality. The August 2025 close approach gave them the perfect window, a rare chance to point serious instruments at 1998 SH2, while it was close enough to Earth to reveal details that would normally be far too faint to detect. Researchers reached out to some of the most capable observatories on the planet. The Canada-France-Hawaii telescope perched near the summit of Mauna Kea, the European Southern Observatory's Danish telescope in Chile, and the Very Large Telescope at Cerro Paranal, one of the most powerful optical instruments ever built. By layering multiple images together, stacking faint signals until something coherent emerged, astronomers finally saw it. A weak, thin tail, barely there, but unmistakably real. Olivier Hainaut, an astronomer with the European Southern Observatory, called it exactly what it was: confirmation. The hypothesis had been tested, and the object had answered. 1998 SH2 was officially reclassified, given an additional designation as a comet, P 1998 SH2, existing now under two identities at once. 27 years of mistaken identity, corrected in a single set of images. Here's where the story stops being about one object and starts being about an entire category scientists are only beginning to understand. 1998 SH2 belongs to a class of bodies called Dark Comets, objects that show the same telltale orbital perturbations as active comets, the same unexplained pushes and drifts, but without any of the visible signs. No coma, no tail, no detectable outgassing that any observatory can pick up. They look, in every observable way, like ordinary asteroids. Researchers have identified two distinct populations within this group. Larger dark comets, following orbits similar to Jupiter family comets, highly elliptical paths that loop in from the outer solar system, and smaller ones, orbiting much closer to the Sun, more compact, harder to catch, easier to overlook entirely. Since the very first dark comet was identified in 2016, scientists have only confirmed about a dozen more. 12 objects, found almost by accident, each one requiring the same rare alignment of a close approach and the right telescope pointed at the right moment. Now consider what that actually implies. The researchers behind this discovery believe many of the larger dark comets in that group could turn out to be regular comets. After all, comets we simply haven't had the right opportunity to observe closely enough to prove it. 1998 SH2 may not be a rare exception. It may be the first confirmed case of something that's been hiding in the catalogue all along, waiting for its moment to be caught. This is where the discovery stops being academic and starts mattering for every single object NASA tracks. Right now, there are nearly 38,000 near-Earth objects in the catalogue, and the vast majority of them are treated as simple gravitational bodies, rocks whose future position can be predicted using the sun's pull, the planet's pull, and nothing else. That assumption is the entire foundation of planetary defense. But comets don't play by those rules. Outgassing perturbs their motion in ways gravity-only models never account for, sometimes subtly, sometimes enough to shift a predicted position by a measurable, dangerous margin. And if an object classified as an asteroid is secretly venting gas, secretly behaving like a comet, then every projection of where it will be in 10 years, 50 years, a century, is built on an incomplete equation. Farnokia has been direct about what this means. Detecting these non-gravitational perturbations isn't just useful, it's becoming an essential diagnostic tool, a way to figure out which objects in the catalogue are hiding a comet's behaviour behind an asteroid's file number. To be clear, 1998 SH2 itself poses no known threat to Earth in the foreseeable future. That was never really the danger. The real danger was quieter than that. It was the possibility that somewhere in nearly 38,000 tracked objects, the math itself has been missing a variable, not because anyone made an error, but because the object never told the truth about what it was. But this story isn't only about risk. Hidden inside these dark comets may be an answer to one of the oldest questions in planetary science: how water first arrived on a young, dry Earth billions of years ago. If a population of icy, comet-like bodies has been quietly drifting through the inner solar system disguised as ordinary asteroids, they could represent a delivery system scientists have been trying to identify for decades, one hiding in plain sight the entire time. There's an even stranger connection waiting here too. In 2017, astronomers detected Oumuamua, the first confirmed interstellar object ever observed passing through our solar system. It accelerated in ways nobody could fully explain, sparking years of debate, some of it wandering into truly speculative territory. Dark comets may finally offer a grounded, physical explanation for exactly that kind of unexplained motion. And now, NASA is preparing to hunt for these objects on purpose. The upcoming NEO Surveyor, the first space telescope built specifically for planetary defense, is designed to find exactly what 1998 SH2 almost got away with: dark asteroids and dark comets that reflect almost no light and reveal almost nothing about themselves until something or someone finally catches them drifting off course. So what does this really leave us with? An object that carried a false identity for 27 years, exposed not by a bigger telescope or a closer look, but by a push too faint for any instrument to see directly, only to be inferred through the math itself. 1998 SH2 was never the exception. It was proof that the exception exists, quietly, inside a catalogue of nearly 38,000 objects we've been trusting to behave exactly as predicted. How many of them are wearing the wrong name right now, drifting just slightly off course, waiting for their own close approach to give them away? The sky we thought we'd already mapped is still keeping secrets, and this was only the first one to slip.